So before I start, I'd like to start with this one. Well, the problem with that one is it's true in many companies, unfortunately. And well, but what is a legacy software actually? Well, usually a legacy software is a software that doesn't have all the fundamental concepts available, or they are not even existent for understanding for all the people working with the software. And there is one common characteristic to most legacy software. It's not it not necessarily is a characteristic, but most of them has it. That is, they have poor quality. And don't get me wrong, I would prefer 1,000 times to have clean code and no documentation at all, rather than thousands of pages of documentation and really bad code. So, but yeah, it's often both combined, then you're stuck. Well, if I step back a bit, now I want to talk about myself. I have been working with software for about 12, 13 years from until now. And I have worked in many industries. I have worked all the way from information system with web applications to C++ embedded and all possible kind of software. So, and if there is one thing all those companies have in common, is that they all have legacy software or had legacy software. Well, the problem is when you have a company where its main system is just software, of course, software always runs in hardware. We all agree on that. But when your software depends on a higher system, it's just one component among many others in a higher system, then you have to try to reason what are the things driving that software, especially that your legacy software, right? Because you need to understand what is behind, what was the reason at any given point in time to develop that software as it is today. And well, when you have a software that is just probably, it's a big software that even if you open that box, you will have a lot of subcomponents within, then it's really complicated to really understand, okay, why is this software looking like this today? So I thought to myself, there are two things I need to do to be able to work further with this software. And that's, well, first, usually when you have a legacy software, you will have pressure from your system to keep maintaining and developing that software in the future. So how can we do that? And I thought we need to answer two questions. First is, what are the important parts of that legacy software to fit with my system context? It means if I have thousands of lines that I have no idea how they work, of course, as a black box, I know what it does. But if I open it, it's just chaos. I cannot use a year to try to reverse engineer the entire software or refactor everything and try to understand every line of the code there, because, I mean, there is no budget that will allow that in any company. It doesn't matter if it's a really rich company or not. And you will have always the pressure to keep maintaining and developing new features in your software. Even it might be that you have a part that is legacy and another part that is not legacy, and they have to communicate still. What are the important parts of that software that you need for the future? What should I put my effort on? And once I have figured that out, then the next question is, okay, now that I know what are the important parts in my software, how do I align now the development and maintenance of these important parts with my system goals, right? So I started doing some research, and I found that there are, I didn't found any paper at all talking about working with legacy software for systems. All the papers I found, all the documentation I found was how to work with legacy software from the pure technical point of view of software. And that's not bad. Of course, there is a lot of good information. There is this really good book, Working Effectively with Legacy Software. I don't know if you know it, from Martin Fowler, one of the big brains in software. But still, that didn't help me because I didn't want to jump into a legacy software and just reverse engineer everything. I needed to understand what was important from it, and there was no paper doing that for me, or helping me to find a way to do that. So then I found, this is quite a long name, this international standard. That's a standard for defining software architecture methods. So most of the most known methods like TOGAF and many others are based on that standard. And that's, I don't know, 200 pages or something. And I read it all, and it has only one line talking about legacy software that says, this may be used for legacy software. And that's it. So, okay, what should I do now? Then I start looking for, I say, okay, systems engineering is known for dealing with complex systems and has solutions for dealing with complex problems when you have systems with many components. So I thought to myself, I should review some of the system engineering architecturing methods that combine software and systems. And then after looking several, I found CAFCR. If any of you have taken any course here at the university here in Kongsberg, you will have met probably someone called Gerrit Müller. He's a brilliant guy. He's the one that created CAFCR, actually, and it's based on the standard. CAFCR, it's a system and software architecture method that allows you to decompose your entire system and software in a sense that you can make sense of it, out of it. So it all starts with subdividing your system in 5 different areas. You will have customer objectives or stakeholder objectives, as I like to call it. Application, functional, conceptual, and realization. Customer objectives is, well, what are the requirements of my stakeholder? What are the key drivers of my system? What my system should do, and therefore what my software should do, right? Then you have application. Application doesn't mean about the application itself. It's about where my system applies. What is the context of my system? Where it lives. Functional. Oh, I missed a C there. Just noticed. But okay. Functional is how my system interacts with the world. I mean, it's still a black box for me, my system, but how it talks to the world. Then conceptual and realization are the 2 last steps, and you can see it as modeling, for example, the actual software or the actual bolt or the actual piece of hardware. And the good thing about CAFCR is it doesn't enforce any way of doing all this decomposition. I mean, you can go with, if you went to this model-based speak yesterday from the Kongsberg group, they were talking about SysML and UML. You can do whatever you want. You can use SysML, UML, or your own drawings. I mean, as I usually think, is any language is as good as the people using it. And if the team doesn't understand UML, then it's worthless, even if you have the best diagrams in the world. But if you have a diagram that you can understand, you can explain, and your team can understand, then it's good. So this is this part here is about actually creating the decomposition. I have tried, this is just an example, we will see it on more detail later. This is more the software and the system, but the next part is about qualities. And the idea is that always you have some qualities that govern your entire software or system, in this case. And the idea is to try to make sense now, after you have decomposed, of what parts of the system and software are being affected or are affecting that quality for the main system. So it's like, I don't know if you have seen on movies or whatever, when people speak in trash on the parks with a stick, it's the same. You grab your quality, for example, maintainability in this example, and you start going through all your decomposition. So, oh, this one here is probably really affecting maintainability. Oh, and this software part is probably affecting maintainability. So we start making sense of things along the entire decomposition of our system and software. And the last part is the reasoning. The reasoning now is you take all your views and you have already made an initial connection here, but now you start reasoning about why this specific software is connected to, through going through all this, connect to this specific key driver or requirement of my system. And the idea is that at the end I had identified why this part in my legacy software, in this case, is so important, or it should be so important for the future of my system. We're going to go into details, but that was the method I decided to use. And based on that, I come to a solution. I say, OK, one thing is to identify the things, but I need a full solution on how to implement this in the long term. So first, as I initially mentioned, it's usually the decomposition of CAFCR. It can be, Kafka doesn't enforce if you are going top-down or bottom-up trying to decompose. And I expect your systems engineer at your company to have pretty much already this composition made for you. If not, probably quit, because then it's chaos. But usually when you go to your software, then you have to start bottom-up, right? Because you don't have any documentation, anything. You just have the code, and you have to start from there up. Then it will be, of course, identifying the main qualities, integrated with those qualities, and at the end, identify the reasoning of your entire system, as I mentioned before. And doing that will give us a snapshot of our system and software at any given point in time. The good thing is that with that snapshot, we can later create a roadmap. The idea is to define a roadmap where, of course, you will have, I don't know, your market roadmap and your system roadmap following that market, and then you will have your software following your system in that same roadmap. It can be a Gantt or whatever. It's not so important for how you do it, as long as you always need to know how are you going to build to the future. And the idea is that you can align the parts of that legacy software you have found are important with the development of your system. So if you know in the future you need to do something in the system that requires a part of the code that is legacy, we don't understand it. We kind of do what it does, but if we open it, we have no idea what's going on in there. Then you can take that part and put it in your roadmap and say, OK, to implement that new functionality for the system and the software, first we need to refactor this part, or we need to understand this part, or we need to whatever we have to do with that piece of software to be able to continue the development. So now we are going to see a very simple example of how to apply all this. So first, I want to explain a bit the example. Suppose you have a machine that all it does is cut boxes out of material. You will have a tool that automatically will cut a box out of a cardboard or whatever. Very simple, not much to think, of course. There's a lot to think if you're going to do a machine like that, but for the example, it's just imagine that part of the system. So first, as I said before, we start with the customer objectives or stakeholder objectives. The thing is, it's called customer objectives because the person that created Kafka, of course, defined Kafka with that word at the beginning, and he agrees with me that maybe it should be a stakeholder objectives, but then he will have to change the name of the of the method. But yeah, that's something else. So the idea is you start, for example, here. You will have to reason. You will have, suppose, these requirements from your customers. And some customer want to have, I don't know, auto tool adjustment. It means you want to cut the box, and you want the tool to automatically be adjusted up and down, for example, so you can cut different materials. OK, that's good. Maybe that's a clear requirement. Suppose it has a lot of definition and whatever, but suppose it's a clear requirement. And then you start thinking, OK, great. But why he wants to have auto tool adjustment? And then you say, oh, maybe he wants to increase automation. Good, good, good. But why? Why he wants to increase automation? Oh, he wants to have productivity. And then we start saying, oh, there is a quality maybe. There is something that is probably one of the key things that should drive our entire system. So even that if your customer is not sure why he wants this, we are trying to figure out what is the main driver of the entire system, because that will help us later to make sense about everything in the system. then we jump into the next section of Kafka, and this will be the application view. In this example here, we have our company, right, or our system, and where is the context, where it's living. And we can see it's, for example, living in 2 different markets. One of them is sample single mapping. You cut a box one time just to make a sample, fine. But you will have also continuous production, and you will say, oh, that's people that want to produce 24/7 with this machine. Oh, wait a second. This makes sense with productivity and increased automation, etc., etc. So, oh, we start seeing some links already. There's one thing here. Also, we found that, well, we already know, we already knew that, but the legacy software we had, it was developed by a consultant company. So be careful with that. But anyway, so we have already some idea. We found that there is another link here. There is something about productivity that is quite important for this system. And then we jump into the functional view. And this is, again, our system as a black box. And the idea is to try to understand everything that's coming in and coming out. For example, materials and boxes. What are the interfaces? What are the restrictions? Maybe there is some environment restrictions that we need to apply, or things that will limit our system functionality that are not necessarily the requirements of the customer. So then we can open the box, stick our head in, and start looking into the engine of the system. And we will have many models. I expect your systems engineer ready to have a lot of these models. You will have physical models, logical models. So you will have define of how to produce a box in a logical way. So you will have actions you have to perform, things to control, and algorithms to run. The details there in these boxes is not so important right now, but the point is to try to see from the system perspective how the system should work or how the system works. So later we can connect this with our software, with our legacy software, but we have no idea how it works. So as I said before, now we have to take a look at the legacy software, but from the legacy, we need to start bottom up. So there are many ways of doing it. There are many papers helping you. You can do unit testing, you can break dependencies, you can refactor code or whatever. I would say the easiest is just to run the machine, trace your code, and you will start seeing, oh, this part here is probably very important for, it's probably running most of the production. This other part is probably controlling the tool. And you don't understand how that module of your software works, but at least you know that that part there is doing something useful for your system. So you will end up probably having some model of your software that in detail you don't understand. You don't know what's really happening in there or in there, but more or less you will start seeing part of your software that are critical for your software. You still don't know which of those yet are the most important or those that you should focus on, but it gives you an idea. And then you can go, as I say, bottom up. And now we can create, for example, a functional model of the software itself. So now we have the function of produce a box from the software point of view. And we can see the different algorithms, the things to control, or the operations you have to perform. So, well, now we have understood how, more or less, from the software point of view, producing a box will work. And we have how, from the system point of view, producing a box will work. And, well, now we can start making some links, right? We can kind of see, we are already starting to see what parts of my software should I focus on. Still not sure. I kind of can see where, but still not sure. So then we jump into the qualities. I expect your company already had identified what are the qualities of your system, but if not, you can have done the previous decomposition and found more or less which ones are the important. In this example, we will focus on productivity. So we can find here that there are many qualities affecting a system, of course. Any real life system will be affected by many qualities, but there are always some that are more important than others. So if we take productivity, then we can say, we take our productivity stick and start going through all the decompositions we made in our system. We can start going, I don't know, process automation, production speed, the continuous production market, and I don't know, material recognition, controlling a feeder of material, and then we come to the software parts and we see, I don't know, this specific part, for example, of the software is really affecting how this quality performs in our system and our software. So then we need to stop and start thinking. We jump into the last part of CAFCR and say, we need to now make reason of everything we have found so far. So this is when you get all your team together in a room and start discussing what should we focus on in our software. And the first step is a 5-step, how can I call it? 5-step part. The first step is just to try to define where are you going to start discussing? Where do you want to start focusing to try to make reasons? So we decided to start on the link we generated before between the system function and the software function and how they connect together and how this will open for us to identify software and system parts that talk together. So we can see the light blue lines. Those are to identify weak links between the different components or views. And the thick blue lines are for identifying the critical links. So 2 things that if you don't have that part on the software, then nothing will work, for example. And the red one is just to how the thinking process went around in the reasoning. So after you have done the first part at the top there, you have to go to step 2 and create more insight. So first you started with a few views to try to start discussing and see where are we going with this. But then in the second one, you start throwing most of the views at these 2 levels. So you will start throwing software components here, and there probably you have already created some models of them. And also some system views, and try to start discussing how they all interconnect to each other. So now you have already started figuring out most of the links between your system and software. But even that you figured that out now, you still don't know, even that you have strong links here, not necessarily that's important for your system. Maybe that's important for that component of your system, but not for your system goal. So the next step will be to deepen the insight. So it will be to open a bit more here and start adding more views from higher levels of the architecture to broaden the discussion. So now you will start seeing, okay, this part of the software now connects to the input of materials to my machine, for example. Or the output, or this specific restriction that I need to have, otherwise I cannot release my system. And then we have the step 4, then it will be fully broaden the insight. Now we take our key drivers of our system and try to make sense all the way to the very bottom part of our legacy software. So now I can say, for example, that this specific part here is important for the tool path calculation of how to cut the bugs. And then this is important for producing a box functionality and how materials are coming in. And it's really affecting the continuous production that I need to achieve and the production quality and the increased automation, for example. no, not this one here, but this one here. So, wow, now I have a full link of my system goals towards my legacy software. I still don't understand how the legacy software works. I just know that there are parts there that are doing things that are important. At least I have figured out now what are those important parts in my legacy software. So then at the end, you start removing all the weak links to try to see actually what are the important parts. So you will figure out, okay, this part, and this part is the most critical. Oh, did I press something? No. It's the more critical path or components in my system. So to achieve this, I hope you can have very proactive systems engineer and software architects that can talk together, can talk to the team, and can all kind of agree all together in how to discover this. I mean, because I expect most of this already exists, right? Because otherwise then you have a full legacy system. But yeah, the idea is just to discover the parts in the software that I should put my focus on. And well, then we will have to create a roadmap. And as I say, a roadmap can be anything from a simple, this is just an example of a roadmap. You can have a Gantt, or you can have critical path, or you can have anything that tells you how are you going to evolve and develop your system in the future, and your software, of course. So in this example, we may have the market and how the market is evolving, and then you have a system that is defining how the system will evolve in the future to fulfill the market needs. And then you need to have a software architect that is able to follow up this roadmap with a software roadmap. What is important here now is we have identified what are the important parts in the legacy software that we really need to focus on. So if the system needs, for example, I don't know, it wants to create a robot. It will be a robot for feeding materials into your system. And you know you have to do something in software, of course, to cope with that robot. But you have learned already that to do that, you will have to go and take a look into the legacy software that controls that part or interacts with that part of the system. And you have to put in your roadmap, okay, first we need to, for example, in this example, redesign this part of the software before we can even start implementing whatever is needed to fulfill that need. And so on in the future. So now you didn't waste many man hours on try to understand a full legacy software, but you can just focus on those parts that you should really be focusing on. And then you can really reduce the scope of your refactorings or understanding or modeling or anything you need to do to cope with the legacy software from the technical point of view. So yeah, I think I went a bit fast, but this paper is already published. You can get it from there. If you want to read it on full, it's 15 pages, if I remember correctly. If you go to that link, you gotta pay to download it. But if you send me an email, I can send you a free copy. So I don't know if you have any questions. No? Well, then, thank you, everyone.